Okay, so Bayesian methods. Let me give you another example on Bayesian methods. Yeah. So it is like this. Again, we have a coin. Okay, so, well, it's not too much information in a coin, but that's okay. So, and so we toss it 15 times. And we get how many times? 10 heads. Okay, so that is what we have. Well, let me. Yeah. In fact, the one that I have here and I have calculated, it is a little different. So let me go with these numbers because I have done calculations. So it is 20 times and 12. So a little different. Let me drop that. Well, we just make this a prior assumption. So what do we have first? First of all, we have, let me write it, we have x is number of heads, and we know this x is binomial, and here we have 20 and p. So the prior should be on p. So distribution, prior distribution for p we have this p of h. We say it is 1/2, and with probability say point. Say, well, we think that it is not fair. So let's say it is with probability say 0.3. And p of heads, let's take this 12 over 20. So 12 over 20 with probability is 8.7. So we want to see which one really is better. Okay, so what do we do here? So this is the p. This is the p. So let's first find p of h. X is yeah, in fact the h itself. So let's see, we have p of x is 12. That is, we have 20, 12, p to power 12, 1 minus p to power 8. Okay, so that is, but what is p of x being 12? P of x being 12 is p of x being 12 given the small p, this thing is 1/2, the probability that small p is 1/2 plus p of x is 12 given the small p is 12 over, well, let me just write 12 over 20. P of p is 12 over 20. Okay. So what is this? Let me calculate this for you. So this one is 12, 20, sorry, over 12, and that's 1/2. So I have 1/2, 12, 1 minus 1/2, 8 times 0.3 plus 20, 12 times 12 over 20 to power 12, 1 minus 12 over 20 to power 8 times 0.7. Okay, so let me erase all these things and continue here. So let me calculate. I guess I still have this thing open here, the R, so and 20, well, I guess 12, size is 20, and probability is sorry, probability is 0.95, and we haven't got 0.8684. So let's continue here. So that's 0.8684 times 0.3 plus. The other one is the same, except that is 12 over 20, 0.5841. So let's see what it is. And 1 times 0.7, 0.6693. So that is when we assume this distribution for small p, that is probability of getting an H, heads, I will find this. So that is 0.6693 with this distribution. Now, let's find the posterior. So the posterior is in fact this. We go back the other way. So we just want to find probability that small p is 1/2 given x is 12. Right? Given x is 12. So that is p of x is 12 given small p is 1/2 times p of small p is 1/2 divided by p of x is 12. This is why I need that. X is 12. This is in fact a denominator here. So this one is in fact this guy here, 0.8684 times 0.3. Let me erase this. Mixed up. Divided by 0.6692. And look at this, this will be less than 1. Because this is the summand here. This is this added to this gives me this. So if I divide this by this, I will get a number between 0 and 1, right? In fact, it's less than 1. It's positive and less than 1. So let's find it. Divided by 0.6693. 0.3892. And the other one, P of P is 12/20, given that x is 12, is the other one. So that is in fact 0.5841.7 over 0.6693. Point 6108. Okay, so the posterior distribution with that prior gives me this, the probability of H being 1/2 is now 0.3892. Probability that H is 12/20 is 0.6108. Well, remember it was 0.3 and 0.7. So the prior was this, 0.3 and 0.7. So this, in fact, assumption, not this assumption, say this experiment. This experiment is telling me that it's, in a sense, the probability that P of H being 1/2 is higher than what I was thinking, given this experiment. Okay, so that's given. But you might ask this question, why did I choose this thing? Why 12/20? Well, I just looked at the problem. It said 12 out of 20. Okay, so 12 out of 20 was it could be just a guess. Like I don't know, maybe saying that an educated guess or what. I don't know. So, anyways, that is in fact what I saw. You might say, okay, if you are saying that it is unfair, maybe I should have chosen like 8/20 rather than 12/20. That's one way to say. It means that well, we can say that that's just too pessimistic, saying you have 12 heads and you're thinking it favors the other one. I don't know, just no. You might say, okay, now can I make some decision here? can I say, okay, based on what I see here, well, you can continue tossing the coin like 100 times, say, and see what happens. You can do that at home, just toss a coin like 20 times and see how many times you get heads. And then you can do this calculation here. But what bothers maybe anyone is this second assumption. I mean, this is okay if you are just checking this, that it is fair or unfair. So you are checking whether it, not checking whether it is, but you are, have this as one assumption here, that it is 1/2. So things like this come down to, if it comes down to making decision, because what are you doing here? Is it just for fun? Or you want to make some decision? You want to say, okay, I am going to use this in a game. I'm like working in a casino or something, or like a referee in like a game, like a football game, say. They toss a coin at the beginning. So you have to decide whether this coin is fair or unfair. Because say maybe the team that starts usually wins. Like if you are playing chess, for example, the one that starts first most often wins. So so it is important to. I'm not saying they toss a coin, but I mean, yeah, it's important in like some sports who starts first or who makes the first move, say. So that comes down to what we call test of hypothesis. So let me write it down and discuss it to some extent and maybe give you an example or examples next time. So test of hypothesis is something like this, something like saying, I think that the coin is fair, which means that small p is 1/2. So that's your hypothesis. So that's what we call the null hypothesis. Versus what? Like the second one, which I assumed, 12/20, is like the one that we call alternate hypothesis, or whatever you call it. I mean, those are the terminology they use. So you're basically having two, say, hypothesis, which you call it H0 for null, and the other one alternate. So this is called null hypothesis and alternate. Now, there are different ways to approach this. One of them is that frequentist method, which has been around since 100 years ago, something. And people who were responsible for that, especially Pearson, was. But then at some point, people who were doing Bayesian statistics, or even students, or even people who practice this, or they practiced that frequentist approach, they most often when you start that method, you really get confused. You just go nuts and say, what are they talking about? What is this saying? What very famous or infamous p-value? It heavily relies on logic, so it's more logical than, definitely you calculate something, but based on your calculations, you say something. So at some point, one might just ignore that and say, okay, who cares? I just find the p-value, that's what they want, and based on that p-value, I just say I reject the null hypothesis in favor of the alternate one. So I reject H0 in favor of H1. That's how they say it. Or the other way, which logically makes sense. That's what they should say, in fact. But in Bayesian method, we try to do something else. Let's say I think it's more numerical. So well, the other one is also numerical. You're calculating some probability p, but here, to me, it makes more sense to do something which is different from that. So what we have here is, in fact, something like this. So let me write down. So we have H0 and H1. Choose H0, H1. Assume each happens with probability 1/2. So you see, these are like events. Choose this. So that's 1 with probability 1/2. So you assume that hypothesis H0 happens with probability 1/2, or the other one happens with probability 1/2. So B is gather, or 2 is gather evidence. Oh, this looks right. Let me choose gather evidence, and to experiment or data collected. Okay, and let's call it. So this evidence somehow is like some data you have. And 3 is so this is what we do in Bayesian method, Bayesian test of hypothesis, and this K is something which, to me at least, it makes a lot of sense. So that's probability of H0 happening given the evidence divided by probability that H1 happening given the evidence, right? So if I write this, if I use the Bayes' formula, then quick try. This top one is in fact this. It is P of E given H0, P of H0 times divided by P of E. And this one is P of E given H1 times P of H1 divided by P of E. Right? So, what are these two, H0 and H1? 1/2. E and A, they cancel out. So basically this is 1/2, this is 1/2. And so this one and this one cancel out, this one and this one cancel out. So we have this. P of E given H0 divided by P of E given H1. So this depends on this. See? So that is called Bayes' factor, K. So you're saying this thing. In fact, this K, there's like a chart for that, that if K is this much, then there is hard evidence. If it is this much, there is not too much evidence, and blah, blah, blah. I will post that for you. But this K, in fact, is telling me something. So if K is less than 1, for example, is less than 1, then this is less than this. So it's saying that the probability of this happening is less than this one happening, which means the probability of this evidence happening given H0 is less than the other one happening given given H1. If it is bigger than 1, then this one is bigger than this. So your hypothesis is kind of in a good position, saying, you see, my hypothesis makes more sense. But how far should this be above 1? Is it like being 5, 6, 7, 10, 100 something? Well, that one is just experiment. I don't think there is too much theory about that. But there are, like, depending on the person, you might say, okay, if this is like for me, if it is like around 10, for example, then that's okay. I mean, there is enough evidence to say that H0 is acceptable. Well, you might even use the terminology or the used for the other type of hypothesis testing and say we accept or reject H0, or say we reject H0 in favor of H1, or we accept H0. But anyway, now, in situations like what we had with the coin, let me erase this thing. So with that coin, what would be a good H0? So with the coin, so test of hypothesis for the coin. So you can say that P of getting heads, P of heads, let me write head, not H. P of heads is 1/2, with probability 1/2. What is the other one? What is the other one? So you can say, why should I just choose one probability that is like one number for that? And you might say, okay, if I have to do that, then I have to do that to more than one number. You can say, okay, yeah, the other one can be P of heads is either, say, 0.2, either over 3, or blah, blah, blah. You can do that. But if you say P of heads for this situation, if you say P of heads is, you might say, okay, I don't want to write 12 over 20, whatever that was. It's either this, or this, or this, or this. Well, 0.5 is here. 6, 7, 8, 9. You might say this, or. But then, that makes things much harder. I mean, to say that it's either this with 1/2, that's like a little hard. Or you can say how many. You have 8, so you can say each one of them with 1 over 60, something like that. But what is the better way to say this? So if X is heads, then you might assume that X, in fact, is has uniform distribution, 0, 1, which means that probability of heads, that's small p, in fact, is not any number between 0 and 1. You can even, well, there's no, I mean, it can be 0. 0 means what? 0 means the coin is two-sided. The two sides are like both, let's say, tails, something like that. So or 1 is the other way around. But anyway, so you can say this, and this makes more sense here because it's much better than saying I think P is 8.4. You're just saying that I don't know anything. I basically have no idea, and this P can be any number between 0 and 1. And remember, P is probability, so that is in fact a number between 0 and 1. So I can say that this P, in fact, has uniform distribution, and it is a number between 0 and 1. Okay? Now, so if I just go back to the problem, which was like, remember it was the probability of x is like 12, the problem that I just solved, then it was P of x is 12 given P is blah blah. So I have to write something like this, P of x is 12 given that P is 1/2 times P of P is 1/2. But the other one is a little bit harder, because this says that this P, in fact, has a distribution. It's uniform 0, 1. And the probability that P is uniform 0, 1 and 0, 1. But this is in fact 1/2, right? We assume that this is 1/2. So that's okay. There's nothing special about that. But this one we know, but what is this? So that is in fact when you have a probability. I mean, you have distribution with some, say P in this case, and this does not have a discrete distribution. So the parameter does not have discrete distribution; it has a continuous distribution. So what do we do when we have continuous distribution? So that is in fact something which I will not discuss now, and I will do it next time for you. First I discuss this, what is this thing, and then I will give you an example of this type, and the hypothesis testing, which I guess is much easier. The Bayesian one is much easier to understand than the frequentist one. So let me stop at this point, and I will continue this thing next time.